So, I mean, we've all been taught the Einstein version of time, right? Like, you picture it as this four-dimensional fabric.
Right, the classic space-time continuum.
Yeah, exactly. And it bends, it stretches, it slows down depending on, how fast you're moving or how close you are to a massive planet. We just kind of treat time as this grand cosmic architecture that dictates everything.
Well, it is the bedrock of modern physics. I mean, it feels elegant, it's highly geometric, and it really relies entirely on this assumption that time itself is a physical dimension that you can warp.
But then, you open up the stack of theoretical physics papers we're diving into today, and that beautiful 4D fabric is just, it's ripped right out from under us.
Oh, completely. It's a total paradigm shift.
Yeah, because the framework we are exploring for this deep dive suggests time is actually an absolute unbending parameter. Like, it doesn't stretch, it doesn't warp. Time is just constant.
Which completely redefines the landscape for anyone studying physics. Uh, these sources are arguing that time itself never changes pace.
Yeah.
So when we observe time dilation,
Like when a clock ticks slower in space versus on Earth.
right, exactly. When we see that, it is purely the physical mechanism of the clock that is slowing down. It's just reacting to its environment.
Which is, I mean, that is a massive claim to make. So our mission today is to unpack this specific framework. It's called Postulate X2, the electrodynamic origin of time dilation.
A bit of a mouthful, but
A bit, yeah. But we are going to explore how the slowing of clocks might actually just be driven by changes in the density of the vacuum of space. And the part that really shifts this from abstract theory into something you can touch is that researchers have drafted actual experimental blueprints.
the actual laboratory blueprints, yeah.
Right, to artificially pause, slow down, or even fast forward decay right here on a lab benchtop.
And I think the implications for you, the listener, are just profound here. Because if time dilation is a purely electrodynamic phenomenon,
Meaning it's driven by electromagnetism.
right, driven by electromagnetism rather than the, untouchable warping of a space-time continuum, then we don't need a black hole to manipulate it.
Yeah. We don't need a spaceship traveling at the speed of light. We can engineer time dilation right here on Earth. We are essentially taking it out of the cosmos and putting it into the hands of engineers. So to figure out how to, manipulate time in a lab, I feel like we first have to understand what is physically happening to an atomic clock when it just sits on the surface of a massive planet.
Okay, let's break it down.
Because the classic general relativity example is that a clock here on Earth ticks slightly slower than a clock just floating out in deep space.
Right, and under the standard model, the Earth's mass curves space-time, placing the clock deeper in a gravity well, which supposedly, stretches time.
Right.
But postulate XT2 offers a totally different mechanism. In this view, a gravitational field isn't a curve in space at all. It is simply a region of dense vacuum polarization.
Dense vacuum polarization. Okay, let's pause there and break that down. What is actually getting denser in a vacuum? I mean, isn't a vacuum supposed to be empty?
Well, you'd think so, but it comes down to a property called the electric permittivity of the vacuum.
Okay.
Think of permittivity as a measure of how much resistance a medium offers to the formation of an electric field within it.
Oh, like electrical friction almost.
Sort of, yeah. And the massive accumulation of matter on Earth-like, the billions of tons of protons, neutrons, electrons, it significantly increases the effective electric permittivity of the local vacuum around our planet.
So the vacuum of space isn't just empty nothingness. Near a giant rock like Earth, the vacuum itself literally gets thicker.
Yes, that thickness is the key. Because the vacuum on the Earth's surface is a thicker dielectric medium, it physically compresses the absolute energy gradients between the electron shells.
Inside the atoms.
Right, inside the atoms of any object sitting there, including our clock.
Okay, let me make sure I'm visualizing the clock part of this correctly for the listeners. So an atomic clock measures time by counting the incredibly fast vibrations of an electron as it leaps between different energy levels, right?
Exactly. It's essentially a subatomic metronome. And when an electron leaps down an orbital level, it releases a photon of a specific frequency. And that frequency is the quote-unquote tick of the clock.
Okay.
But the energy required for those atomic orbitals to even exist is fundamentally dependent on the electric permittivity of the space separating the electron from the nucleus.
Ah, I see. Since the Earth has thickened the vacuum, the physical space the electron is jumping through has more resistance.
Exactly.
So the energy gap between those electron shells is physically squished.
Squished is a great word for it. When the electron leaps between these compressed orbitals, the energy difference is smaller. And a smaller energy gap means the photon it emits has a lower frequency.
Wow.
So the physical mechanism of the atomic clock is what slows down. Time itself is marching on at the exact same rate everywhere.
So it's like trying to run underwater versus running on a dry track.
That's a perfect analogy, actually.
Right, because the runner, in this case, the clock physically slows down because the medium they're pushing through is thicker. It offers more resistance.
Right.
It isn't because the fundamental concept of distance suddenly warped around the runner. It's just harder to move.
The physical resistance of the medium dictates the speed of the mechanism.
Okay, I buy the gravity argument. It makes complete mechanical sense. But what about speed? Because we know astronauts age slower when they travel extremely fast.
Right. Kinematic time dilation.
Exactly. And we know from particle accelerators that if you shoot a highly unstable particle to near the speed of light, it suddenly just refuses to decay. It lives much longer.
It does.
But there is no massive planet thickening the vacuum inside an accelerator tube. So does this framework just fall apart for moving objects?
No, it doesn't fall apart at all, but the mechanism does shift. So we move from gravitational time dilation to kinematic time dilation.
Huh.
And to understand why a fast-moving particle lives longer, the sources introduce a really fascinating concept called vacuum rogue waves.
Vacuum rogue waves. That sounds like a surfing term, but applied to the subatomic world.
It kind of is. It's a highly chaotic phenomenon. Because in this framework, spontaneous particle decay like a radioactive isotope suddenly falling apart and emitting radiation.
Right.
It isn't actually spontaneous at all.
It's really.
Really. The decay is actively triggered by the chaotic bombardment of background vacuum fluctuations. Those fluctuations are the vacuum rogue waves.
Okay.
They are constantly crashing into the boundaries of particles, and eventually a wave hits hard enough at just the right angle, and the particle shatters. It decays.
So an isotope is basically taking a microscopic beating from the vacuum itself until it finally just breaks.
Exactly. It's an environmental effect. But when a particle accelerates to relativistic velocities, something really dramatic happens to protect it. Its intense, self-generated azimuthal magnetic fields start to compress its transverse boundaries. Wait, hold on. Azimuthal magnetic fields. Are we just talking about the magnetic field that wraps around a moving charge?
Yes, exactly. Azimuthal just refers to the circular magnetic field that forms around the direction of travel.
Oh, got it. So as the particle moves faster, its electric charge is moving faster, generating this incredibly intense magnetic field wrapping around it like a cylinder.
Okay.
And at extreme speeds, this field becomes so powerful that it deeply polarizes the local vacuum layer immediately surrounding the moving particle. It generates a dense dielectric shielding sheath.
Oh, wow. So the particle isn't traveling through a stretched timeline. It's literally generating an electromagnetic deflector shield out of its own speed.
Exactly. And because this dielectric shield is so dense, it physically repels those chaotic vacuum rogue waves we talked about. So the particle is taking far fewer hits from the turbulent background vacuum.
And fewer hits means it takes much longer to break apart. It lives longer because the deflector shield is protecting it from the environment.
Precisely.
Man, that makes a highly abstract concept feel incredibly mechanical, like it's just engineering at a subatomic scale.
And if we accept this premise, that time dilation and lifespan extension are simply electromagnetic shielding and vacuum permittivity effects, it opens up a completely new frontier of experimental physics.
Right, because we no longer have to be passive observers.
Exactly. We don't have to hope to find a fast enough rocket or a heavy enough planet.
We can put time on the laboratory bench. If nature slows down clocks by thickening the vacuum or, extends lifespans by putting up magnetic deflector shields, we should be able to artificially engineer those exact same conditions.
And we can. The sources outline 3 highly specific blueprints for doing exactly that.
Yes, let's get into those.
The first one is what they call the artificial gravitational well. And this is a direct test of the gravitational time dilation mechanism we just broke down.
Right, so how do we test gravity without gravity?
Well, the setup described in the papers uses a high-precision optical lattice atomic clock, specifically a strontium-87 clock.
Which is, unimaginably precise.
Unimaginably. So they put this clock inside a highly evacuated vacuum chamber. But the chamber is sandwiched between 2 massive superconducting capacitor plates.
Okay, capacitor plate.
Yes. The goal is to generate an extreme, static, continuous electromagnetic field across the vacuum chamber. We are talking about pushing the absolute maximum limits of modern laboratory engineering to create a localized field of immense power.
So what happens to the seemingly empty vacuum when you hit it with an electromagnetic field that strong?
You polarize the local vacuum.
Hmm.
The physical description in the papers relies on the Euler-Heisenberg-Lagrangian.
Okay, let me stop you there. Euler-Heisenberg-Lagrangian. Are we just saying that if you pump enough light and magnetic energy into a vacuum, the vacuum itself changes its physical properties?
That is the core of it, yes. The Lagrangian is just the mathematical model describing how intense electromagnetic fields interact with a quantum vacuum.
Okay, cool.
Because under normal conditions, light waves just pass through each other in a vacuum. But at these extreme intensities, the vacuum becomes a nonlinear medium. The effective permittivity of the vacuum inside that chamber increases locally, independent of any actual mass.
Wow. So we're artificially making the underwater pool thicker without needing an actual planet to do it.
Exactly. And the prediction is that the atomic clock inside the chamber will physically slow down. Its transition frequencies will drop uniformly.
That's incredible.
You have perfectly simulated a gravitational well on a laboratory bench, even though the physical mass of the Earth underneath the laboratory hasn't changed by a single ounce.
So it is a gravity simulator built entirely out of electromagnetism.
Yep.
But, okay, a clock is just a machine measuring frequencies. What about a physical particle that's destined to fall apart in milliseconds? Because we can't just put a radioactive isotope between two magnets and expect it to stop decaying, can we?
No, that requires a completely different approach, which brings us to the second blueprint, stationary kinematic lifetime extension.
Okay.
This is the blueprint for inducing that deflector shield on a physical particle that is sitting perfectly still.
So the target here is a short-lived radioactive isotope, right? Like an alpha or beta emitter that usually decays in the blink of an eye. And we hold it completely stationary in a vacuum chamber using a magneto-optical trap. Then we focus an array of symmetrical, coherent attosecond lasers directly onto the isotope. And attosecond lasers, they fire unbelievably fast, intense pulses of light, right?
Unbelievably fast.
Oh.
And by hitting the isotope from all sides simultaneously, we apply immense ponderomotive radiation pressure directly onto the nuclear boundaries.
Ponderomotive radiation pressure, is that literally just the physical force of the light pushing against the object?
Yes, exactly. Because light carries momentum, right? And when you focus enough of it, it exerts a physical crushing pressure. This pressure artificially compresses the isotope's virtual mass shells.
Virtual mass shells, let's translate that for everyone. Are we talking about the energetic boundaries of the particle itself?
Exactly. Every subatomic particle is surrounded by a cloud of virtual particles popping in and out of existence. The lasers compress this cloud. We're forcing the isotope to generate that dense dielectric shielding sheath without it ever having to move near the speed of light.
It's like taking a loose ball of yarn and squeezing it incredibly tight from every possible angle.
Yeah, good visual.
Right. The denser you pack that yarn, the harder it is for anything from the outside, like a needle, or in this case, those chaotic rogue waves, to penetrate it and unravel the center.
And when that boundary is packed that tightly by the laser pressure, the background vacuum rogue waves just bounce right off. The measured half-life of this stationary isotope will be artificially extended.
That is wild.
It will live longer simply because it is being physically squeezed by light.
Squeezing a particle with lasers to pause its aging process. I mean, it sounds like sci-fi magic, but the mechanics make total sense.
It does.
But are there risks with just turning up the lasers higher and higher to make the shields, impenetrable?
Oh, absolutely.
Yeah.
There is a massive caveat in the literature here. The researchers explicitly warn about crossing what's called the Schwinger limit.
The Schwinger limit, what happens if we push past it?
If the compressing laser field becomes too intense, the electric field reaches a point where it actually rips the vacuum apart.
Rips it apart?
Yeah, it's called vacuum breakdown.
Yeah.
The vacuum becomes unstable, and the pure energy of the lasers is suddenly converted into matter, spontaneously generating electron-positron pairs just out of thin air.
Wait, out of thin air? So the energy's so high that light turns into physical matter, like EMC squared, just playing out right in front of you.
Exactly. And once that vacuum breakdown occurs, the energy is dissipated into creating those new particles rather than compressing the isotope.
Oh, I see.
So the compression fails, and the deflector shield drops.
Wow.
So the ultimate engineering challenge is to squeeze the particle incredibly hard, but stop just shy of the point where you tear the fabric of the vacuum itself.
Precision is literally everything here.
Everything.
Okay, so we can slow time with giant capacitors. We can pause decay with perfectly tuned lasers. But this raises a really fascinating reverse question for me.
Okay, what is it?
If we can squeeze a ball of yarn to protect it and pause its decay, could we intentionally rough it up? Like, could we fast forward the decay of something that is normally very stable?
Oh, the sources confirm you definitely can. They call this process accelerated isotope decay via artificial quantum turbulence.
Artificial quantum turbulence. So instead of a smooth, protective deflector shield created by perfectly tuned lasers, we are intentionally creating a storm.
Exactly. You place a highly stable radioactive isotope, like carbon-14, inside a vacuum cavity. But instead of smooth, symmetrical lasers to compress the boundary, you inject a highly chaotic, nonlinear electromagnetic noise field.
Yeah, the papers describe crossing high-power microwaves and lasers inside the cavity, intentionally throwing them out of phase to spawn localized electromagnetic rogue waves.
Right. You are artificially generating the very waves that cause decay. The researchers are mimicking a phenomenon known as flicker noise. These engineered massive rogue waves repeatedly crash into the isotope, puncturing its subquantum boundaries like the very innermost structural limits of the particle,
Yeah.
far faster than the quiet, natural background vacuum ever would.
And the result is that the decay constant of the isotope spikes. We basically hit fast forward on its internal clock.
Yes.
It ages rapidly, breaking apart in a fraction of its normal lifespan.
It undergoes a highly measurable accelerated rate of decay. Proving you can physically control the decay rate of an isotope with artificial noise definitively shows that decay is an environmental interaction.
Not just a fixed internal timer set by the universe.
Exactly.
And this part of the deep dive takes a wild turn into actual planetary history.
Yeah, this is my favorite part.
Because the Earth might have run this exact fast-forward experiment on us in the past. The sources mention the Lachamp geomagnetic excursion.
Right. So around 41,000 years ago, the Earth's magnetic field essentially collapsed for roughly 1,000 years. Our planetary deflector shield just went down.
And when that magnetic shield collapsed, the terrestrial vacuum was just flooded with solar quantum turbulence. The natural vacuum around Earth became highly chaotic.
The entire planet was bombarded with naturally occurring rogue waves. And according to this framework, that barrage of turbulence would have fast-forwarded the decay of isotopes all over the globe, specifically carbon-14.
And carbon-14 is the exact isotope archaeologists use to date organic artifacts. So let's think about the implications here for a second.
That's huge.
If an organism, say like a tree or an animal, died during the Lachamp event, its carbon-14 was subjected to a fast-forwarded decay environment for centuries. The turbulent vacuum battered the isotopes, making them decay much faster than they would today.
And when an archaeologist digs up a bone from that era and measures the remaining carbon-14, they are assuming a constant rate of decay.
Right.
Because so much of the isotope decayed during that turbulent period, the artifact has what the papers call a phantom age.
A phantom age. So it appears artificially older than the geological layer it is actually buried in. The dirt around it says one date, but the carbon dating says it's thousands of years older, all because its internal clock was subjected to quantum turbulence. It creates these jagged dating spikes in the geological record that just confuse researchers.
Right.
We might literally be seeing the evidence of environmental time dilation in ancient tree rings and bones.
It really forces a complete reconsideration of how we calibrate the history of the planet. I mean, if decay isn't a constant, but a variable entirely dependent on the local vacuum state at any given point in history, radiometric dating requires a completely new baseline.
That is just mind-blowing. We have covered some incredible ground here today. Let's recap this journey for everyone listening.
Sure.
By viewing mass and time through the lens of electrodynamics, we take time out of the realm of abstract, untouchable 4D geometry. We pull it right down onto the laboratory bench.
Right. We can thicken the vacuum with superconducting magnets to slow clocks down. We can use perfectly tuned lasers to shield particles and extend their lifespans by repelling rogue waves. Or, we can use chaotic quantum turbulence to batter those boundaries and fast forward their decay.
Yeah.
It transforms time from a dimension we just passively travel through into a mechanical process we can directly engineer.
And there is one final implication from these sources that really builds on everything we've discussed today. Because if we can perfect the manipulation of these boundaries, what the papers call subatomic phase locks, where we perfectly stabilize a particle's relationship with the vacuum, this isn't just about tweaking single isotopes on a lab bench.
No, it's much bigger than that.
The framework looks toward the future of space exploration.
Because if we can decouple a single particle from the vacuum, There is theoretically no reason we couldn't scale that dielectric shielding up to a macroscopic level.
Right.
The sources propose that future interstellar colonists on massive generation ships could sleep in engineered dielectric stasis pods.
Dielectric stasis pods. So, by surrounding a human biological system with an intense cross-polarized electromagnetic field, their cells would be completely shielded from the background vacuum. The rogue waves would just bounce right off the pod.
They're biological clocks. So cellular decay, radioactive degradation, the fundamental arrow of aging, it would be essentially halted. They would be completely decoupled from the surrounding vacuum as they cross the universe.
It essentially takes the classic sci-fi trope of cryosleep and replaces it with electrodynamic stasis.
Yeah.
No freezing required, just a perfectly engineered deflector shield.
It's incredible to think about.
It really is. So for you listening, the next time you look at the ticking clock on your wall, I want you to wonder, is it really measuring the relentless, untouchable flow of time? Or is it just measuring the thickness of the vacuum around it?